Hello, I'm Dr. Adam Baker from Rocket Engineering Limited and Cranfield University. Electric space propulsion is a way of increasing the exhaust velocity through increasing the energy released in the combustion chamber without increasing the amount of propellant flowing through it. Chemical rockets can frequently be made larger, in principle, any size at all, to give a higher thrust, but eventually the mass of the propellant dominates the mass of the mission. So if you want to do a more demanding space mission, or add more payload, or save weight and ride on a smaller, cheaper launch vehicle, then electric propulsion is for you. To understand electric rocket propulsion, we have to be clear on what chemical rocket propulsion is. So the amount of propellant we can physically store and have to take with us on journeys is the limiting factor of chemical rocket propulsion. It's using the chemical energy stored in that propellant. But we can usually achieve much higher thrusts, for example, in launch vehicle propulsion. In some ways, chemical propulsion is really a controlled explosion. You're releasing combustion energy really, really fast. And you've seen from other classes what happens when that goes wrong. The laws of thermodynamics and chemistry limit the maximum energy we can extract from chemical bond strengths. Hence, chemical rocket exhaust velocities have a practical limit, around 4,500 meters per second, using propellants such as hydrogen and oxygen. And those propellants are already very difficult to handle. Electric propulsion, in contrast, what we do is we decouple or separate the propellant flow from the energy supply, and we increase the energy per molecule of exhaust gas using electrical energy. It gives us a higher velocity and hence a higher specific impulse. Electric propulsion was first demonstrated in the 1920s, but took another 40 years to fly, and actually has only recently become widespread due to the limitations of electric power on spacecraft. It's power limited due to the use of electromagnetic forces to directly accelerate the reaction mass. Although there is a class of electric propulsion we'll look at in a moment, electrothermal, which doesn't do that. So a really simple example is the electrothermal thruster. This is electric propulsion, but what we're doing is using a principle very similar to a kettle. In fact, this is a resistor jet, and a resistor jet is exactly what it sounds like. Using resistive heating of an element, like in a kettle, it transfers energy to a propellant in direct contact with it. There are practical limits to how hot we can make a heating element without using really exotic and expensive materials. And you might remember that C star, which is a big part of ISP, depends on the square root of the absolute temperature. So we can't go too hot. But again, looking at the other part of C star, the molecular mass, which is inversely proportional. C star is inversely proportional to that. Because we don't have to use a chemical reaction to generate the heat, so the propellants don't combine, they don't combust, they don't release chemical bond energy, the exhaust is free from the products of combustion, which in general tend to have higher molecular mass than pure propellants. So if we can find a low molecular weight propellant, which can be heated to a vapor easily, and ideally heated as high as possible in temperature, we can find that, then it'll make a good resistor jet. So work in the Surrey Space Centre in the late 1990s, where I started my space propulsion career, flew the first resistor jets from the UK on missions by Surrey Satellite Technology Limited. These were the resistor jets. They electrically heated a working fluid. A number of different fluids were experimented with. The early resistor jet, as you can see on the bottom left, was really large. Okay, it was about the size of a can of coffee, and it consumed more than 100 watts of power. So it needed a lot of thermal shielding or insulation to get the propellant hot enough and consumed a lot of power on the way. So SSTL realized that adequate performance could be obtained with an easier propellant to work with. So they experimented with butane, C4H10, and xenon. Now, these didn't offer the lowest molecular masses possible, and hence they didn't achieve the highest exhaust velocities, but they could be stored really densely and worked very well for small spacecraft with limited power, which were being pioneered in the early 2000s. And the low power resistor jet that you can see here was very, very small indeed. And it was about the size of my thumb and about the diameter of a tube of Smarties. And several of these were flown on SSTL spacecraft. Now, ALSAT and SSTL's early DMC, or disaster monitoring constellation spacecraft, generated a maximum power of about 240 watts. And in fact, the average power generated while in orbit was considerably less than 100 watts. 100 watts, and that's an old style light bulb before fluorescents and LEDs came into existence. Electric power conversion into thermodynamic energy is also not 100% efficient. So this limits the thrust. In spacecraft, powers can be limited from perhaps a few watts in a really small spacecraft to you might get as many as kilowatts in a larger spacecraft. In comparison, even a small car produces a power of around 100 kilowatts compared to, say, 100 watts on an SSTL small spacecraft. So this limit on available power means that if you're trying to make the fluid move fast, the available thrust is low. And you can see some pictures of the propulsion system here. So that's ALSAT on the left-hand side, being built for Algeria. This is the propulsion system on a panel being put together by one of the Algerian engineers. And you can see an electronics box and two propellant tanks containing butane and valve system here and some pipe work, and then finally the tiny resistor jet thruster there. And the nice thing about this was it was all self-contained on one panel and could be integrated in one piece, tested as a unit, and then popped onto the spacecraft, and if necessary, taken off if anything during spacecraft testing popped up that suggested that propulsion needed a quick fix. Here's the thing, though. The limiting physics of all electric propulsion is this. So that the thrust of any exhaust jet from a rocket engine, doesn't matter if it's electrical or chemical, is m dot, the mass flow rate, times the exit velocity, v with a little subscript e. So thrust equals m dot ve. That's the top equation. Kinetic efficiency, sometimes called neta after the Latin word, is the ratio of the jet power half m dot v squared to the electric power going in. Okay, so that gives you the second equation. If you combine those two, you get the third equation where power equals thrust times exhaust velocity divided by twice the electrical or the kinetic efficiency. Put another way, if we have a given power and we want a high ISP, then we have to accept a low thrust. Or if we really need a high thrust, then we're going to end up with a low ISP. Well, so what? Well, the limits on spacecraft power, especially in smaller spacecraft like the ones I started my career working on at SSTL, meant that in order to benefit from some of the higher ISP performance of electric propulsion, we can only get a very low thrust. In fact, frequently the thrust on many smaller electric propulsion systems is no more than the weight of a single sheet of paper. So about that much. Okay. An electric propulsion system, when you're taking the thruster and putting it into a system, does have some parts in common with a chemical propulsion system. Namely, it's got to have propellant management and storage and a thruster, which turns one form of energy into another. And while even chemical propulsion systems need electrical power, for example, to open valves or heat pipes, the electrical power system for electric propulsion is much more significant, requiring things like a more significant power source, plus power conversion, power transfer, and power conditioning elements. Thermal management is also required, including sensors, controllers, coolers, and often radiators to dispose of waste heat that's not directly carried away by the exhaust. So electric, like chemical propulsion, can radiate waste heat, but its systems, such as power processing units, tend to run at much lower temperature, where radiation is much less effective in space. So you can see how parts are laid out in a simplified spacecraft schematic on the right. it's fair to say that most electric propulsion is much more complex than chemical propulsion as a rule. There's lots going on this chart, probably too many words, but the reason is that electric propulsion has many benefits, and it's hard to distill them down to just a few words. Briefly, it enables more capable missions, greater payloads, more mission level cost savings, and mission lifetime extensions. You could say, if you wanted to argue, that some of these benefits can be delivered by well-engineered chemical propulsion systems, and obviously EP has some disadvantages, such as equipment mass, cost of propellants, and the need for some very careful reliability engineering because the systems are more complex. But EP is used increasingly for large and small comsats, and in fact many other spacecraft to deliver them to orbit, keep them in orbit, and avoid other spacecraft as the skies above our heads get increasingly busier, which is why companies like SpaceX, over on the right, are launching huge numbers of spacecraft, which all have the potential to collide with each other and with other spacecraft. So they really need the efficiency of propellant utilization that electric propulsion thrusters can offer. And that's the Starlink constellation. So the resistor jet was my introduction to electric propulsion. But while low cost, it didn't really take full advantage of modern electrical power and magnet technology to drive electromagnetic forces and accelerate propellant. But on the other hand, simplicity is really attractive in space, where we can't easily fix things if they go wrong. So in other forms of electric propulsion, what we're trying to do is keep things simple whilst not losing the performance benefits, because handling fluids at the low precise flow rates and pressures needed in an EP system is actually harder than you might think. So maybe solid propellant, this is obviously used in chemical propulsion, but in a rather different way. Maybe solid propellant could be attractive for EP. So here's an example of another form of electric propulsion. The vacuum arc thruster. This uses an arc discharge across an insulator between two metal electrodes to produce a plasma that's then accelerated, resulting in thrust. So the metal plasma is produced from the electrodes, micrometer-sized cathodic spots shown in the image bottom right. It's being researched at Southampton University. It's actually one of many forms of pulse plasma thruster which can either use the insulator or one of the electrodes as the propellant. So vacuum arc thrusters have quite a few advantages, as you can see on the left, and they're potentially great for the very smallest spacecraft because of their small size. These are known as CubeSats. However, the thrust is very low, so while resistor jets and many other forms of EP might be producing the thrust equivalent of a few sheets of paper, a vacuum arc thruster this size produces about as much thrust as the weight of a postage stamp. So you're not going to go anywhere quickly using a vacuum arc thruster. And the ISP, although it's better than any chemical system, is not as high as can be achieved by many other EP technologies. But some of the other metrics are good, so this is why this is a promising area of research at the moment. Where are you working?
Hi, so my name is Ben and I'm a PhD student at the University of Southampton studying vacuum arc thrusters.
What kind of forces does it use to kind of accelerate its propellant?
Primarily electrostatic forces, but also electromagnetic. It's a combination. So this is a pair of vacuum arc thrusters. You can see here the two circular thrusters. They're very, very simple, made of three basic components. The anode, which is the kind of square-shaped metal pieces in this pair of thrusters. The cathode, which is at the center of the circle, in this case made of zinc. And then that black ring you can see separating them is called the insulator. And they're all the essential components you need to make a vacuum arc thruster. So a very, very simple electric propulsion device.
We've shown you a couple of different ways to generate the thrust jet, but what all EP needs in addition is a power processing unit, or PPU. In this case, to generate the high velocity jet, we need an inductive energy store, L in the diagram in the middle, which is charged through a semiconductor switch. A signal to the switch can tell that switch when and how often to open, producing a voltage peak L times di by dt, which breaks down the thin metal film coated anode-cathode insulator surface. This cathode arcing generates a microplasma that allows all the current, and hence most of the magnetic energy stored in the inductor, to be deposited into the plasma pulse. By controlling that switching pulse, we can control the energy stored in the inductor, how much propellant is evaporated, and how much impulse bit, or the integral of thrust times time, that we get. However, the overall efficiency of converting electric circuit energy to jet power is quite low, a few percent. And as Ben's going to explain, this, on the face of it, quite simple thruster, like most EP, needs a relatively complex power processing unit, or PPU.
The thruster is very, very simple. The complexity comes in the power processing unit electronics. This is an example of a power processing unit for a vacuum arc thruster here. There's several major components, so capacitors, inductors, and high voltage switches, and they're used to generate different voltages and currents to supply the thrusters with power.
The PPT is another form of electric thruster, which uses the direct accelerating force of electric and magnetic fields to generate an exhaust stream. You can think of it a bit like a vacuum arc thruster with an additional acceleration stage, and it uses an insulator held between two electrodes as propellant to generate thrust. The first stage in PPT operation involves an arc of electricity contacting a fuel, which is normally solid, causing ablation and then sublimation of this fuel into a gas. Heat generated by this arc causes the resultant gas to turn into a plasma, or a charged gas cloud. The ablation expands the propellant plasma at low speed between two charged plates, an anode and a cathode, where it effectively completes an electric circuit, but one not involving wires or physical connectors. The circuit completes because a current can flow through this plasma, electrons or charge carriers going one way and ions going the other way. So this flow of charge carriers generates a really strong electromagnetic field, which then generates a force known as the Lorentz force on the plasma. This accelerates it out of the PPT as a high velocity plasma jet. I suppose you could think of this as a kind of plasma railgun. The pulsing occurs due to the time needed to recharge the plates following each burst of fuel and the time between each arc. This frequency of pulsing is normally very high, so it generates an almost continuous smooth thrust. While the thrust is very low, a PPT can operate continuously for extended periods of time, yielding really high delta Vs. So several PPTs have been flown in space since the 1980s, and there's lots of research around the world on ways to improve their efficiency and scale them up. Now, the mag drive thruster uses the most modern electrical engineering techniques, drawing on plasma physics and pulse power systems know-how derived from the fusion energy industry to deliver a multi-kilo amp, 1000 amp, and megawatt class electrical current pulse to the plasma injector, where a small amount of solid metal propellant is vaporized into a plasma and accelerated to high velocities. So this is called a shot. Operating at high frequency, these shots or bullets of plasma are passed through a magnetic chamber, which accelerates and directs the plasma exhaust, producing a high thrust at high specific impulse. It's even possible to steer the thrust or vector it. Mag drives are starting to be tested in space, and their scale-up is currently being researched at the Mag Drive factory in Harwell in Oxfordshire. And as you can see from the bottom right, mag drives are extremely compact, great for small spacecraft. So I've gone to the mag drive factory to find out more. So mag drives, and I'm holding an example, are compact and inexpensive, very easy to integrate, and pretty much as close as you can get to a plug-and-play spacecraft propulsion system. Mag drives are designed to enable agile maneuvering of the next generation of spacecraft. Mag drives offer versatile, customizable performance. We can work in eco modes, very high specific impulse or propellant utilization efficiency and slightly lower thrust, or we can offer much higher thrust for rapid maneuvering at the expense of specific impulse. Mag drives operate on safe, inert and unpressurized metal propellant stored at high density, enabling them to be extremely compact. The first mag drive in-orbit demonstration, this unit here, is going to be in mid-2025. We'll be receiving some flight data after that. Pretty sick, hey? Well, it just gets better. The Super Mag Drive is currently under development at MagDrive with support from the UK Space Agency. Super Mag Drive aims to be able to generate thrust up to 10 newtons with a performance as good as or even better than current state-of-the-art electric propulsion systems. Super Mag Drive is also specifically being designed to be refuelable using metal sources found throughout the solar system, on or in asteroids and the rocky inner planets, perhaps extracted from defunct satellites as a form of future recycling. Further developments of the Super Mag Drive might even use high-temperature superconducting magnets to achieve really much larger levels of performance. While we're waiting for the Super Mag Drives to be developed and give us spaceship maneuverability like we saw in The Expanse, I need to tell you about a couple of other forms of electric propulsion which are very commonly used today. So this diagram is a graphic from 2012 showing what one company had powered with electric propulsion. It's quite a few spacecraft. If you look closely and follow the key at the bottom left, you'll see a lot in yellow, red, and green. Now, although things have changed a lot since 2012, the technology hasn't. So the next section is going to tell you about the most common thruster in use today, the Hall effect thrusters on the left. These plasma thrusters form the bulk of electric propulsion used today, having matured over several decades from some originally Russian designs. Starlink constellation from SpaceX uses HETs, so I can confidently say there are several thousand operating in one orbit above me right now, and they offer a good balance of thrust and ISP, or ability to maneuver fast and efficiently. Their cousins on the right are a bit more exciting. It's a bit like comparing Ferraris to Mini Coopers. Both are obviously exciting to drive, but one is really in a different class to the other. And these are the gridded ion thrusters, which have seen a lot of use on deep space missions and in very low Earth orbits. So the Hall effect thruster. Do you remember the pulse plasma thruster from a few slides back? Making use of an electric current running through a plasma to complete an electric circuit, generating a magnetic field, which in turn accelerated the plasma out of the thruster. That's the Lorentz force at work, and it can be applied in a rather different way to create thrust. So what the Hall effect thruster does is it uses a different manifestation of electromagnetic forces, the Hall current, in which the charge carriers, that's to say a flow of current, in a magnetic field experience a force. This force makes electrons from an electron gun, that's the cathode neutralizer at the middle top of the picture above, move in a tight spiral path inside the thruster. These ionize an incoming neutral gas from the left that comes in through the anode. That might be xenon or increasingly krypton or argon because they're cheaper. There's an electric field inside the anode chamber, which is made of a robust ceramic material, something like boron nitride. And this field expels the ions created as a high velocity jet. Although again, the thrust is still relatively low, only a few sheets of paper worth for a typical thruster. But again, in space with no air to cause drag, these small thrusts can provide very economical delta Vs, and many satellites currently use these Hall effect thrusters or HETs. Now, HETs can also be made really small. The video on the right, drawing as little as 100 watts from the spacecraft, although the lower the power, the lower the thrusts, common challenge in EP. Have a look at this next video from some of the world's experts in electric propulsion, the Plasma Dynamics and Electric Propulsion PEPL laboratory at Michigan University in the United States.
Hall thrusters are a widely used type of spacecraft propulsion device. Instead of combusting a chemical fuel like a typical rocket, Hall thrusters employ electricity to ionize a propellant, which can then be accelerated by an electric field to produce thrust. This produces much less thrust than a chemical rocket, but is far more efficient, enabling missions which carry more payload for a fixed launch mass, and which in some cases can even be faster than those launched by a chemical rocket. Let's take a look at how one of these devices works. Hall thrusters have only a few key parts. There is a discharge channel, typically made of a ceramic, a metallic anode, and a hollow cathode. To start the thruster, we apply a voltage between the anode and the cathode. This sets up an electric field, which causes electrons emitted from the cathode to migrate toward the anode, completing the circuit. Electromagnets embedded in the thruster produce a magnetic field perpendicular to the electric field. Since electrons orbit magnetic field lines, this field acts to halt the electrons on their path from cathode to anode. The combination of crossed electric and magnetic fields also induces the electrons to rapidly circuit the thruster at speeds approaching and even exceeding 1,000,000 miles per hour. This so-called Hall current gives the thruster its name. At the same time, a neutral gas, typically xenon or krypton, is injected at the anode and begins to diffuse downstream. Ever so often, a drifting electron impacts a neutral atom. Sometimes these collisions have enough energy to knock an electron off of the neutral atom. This produces a positively charged ion and a second electron, which joins the Hall current. The more electrons there are, the greater the probability of collisions, and in this way, more and more ions are produced in a process known as avalanche ionization. The resulting fluid of ions and electrons is known as a plasma. The positively charged ions in the plasma feel the applied electric field and are accelerated downstream at tens of thousands of miles per hour, producing a small amount of thrust. Enough electrons follow them such that the device remains electrically neutral overall. Every time an electron collides with a neutral or an ion, it loses a small amount of momentum and drifts a bit closer to the anode. In this way, the electrons are able to complete their path from cathode to anode despite the presence of the magnetic field. However, the electron current that actually reaches the anode is much higher than what we would predict even when accounting for all types of collisions. The cause of this enhanced, so-called anomalous transport is unknown and is an active area of research. However, as a result, we cannot simulate these devices in a way that predicts their thrust, efficiency, and other key performance metrics from their geometry and operating conditions alone. My research at the University of Michigan's Plasma Dynamics and Electric Propulsion Laboratory focuses on improving our ability to model anomalous electron transport in order to build predictive simulations of Hall thrusters. Many research groups attempt to capture this critical phenomenon via high-fidelity, three-dimensional particle-in-cell simulations. However, such simulations take months to complete on thousands of CPU cores, making them highly impractical for most engineering design purposes. Instead, I am focused on developing simpler models of the anomalous electron mobility that can be implemented into fluid simulations which may run in a matter of hours. Without predictive models, developing a new Hall thruster must instead rely on lengthy and expensive ground tests in a vacuum chamber. With better models, we can more accurately predict how a Hall thruster will operate in space, opening the way for more rapid simulation-based design optimization and reducing the cost of prototyping, testing, and qualifying these devices. This will in turn pave the way for developing new generations of Hall thrusters, which can operate at both very low and very high power levels, employ exotic propellant gases, and even use unconventional magnetic field shapes and geometries. With such improvements, these thrusters might be used to take humans to Mars and beyond.
The gridded ion thruster, or GIT, perhaps better referred to as an ion drive, is one of the highest performance, in ISP terms, of electric propulsion. However, its operation is based on a very simple idea. Ions are formed and accelerated away from a spacecraft by an electric field, purely electric, held between at least two permeable grids or meshes. Depending on the grid geometry and the field strength, the ions can consistently reach a very, very high velocity, easily 30,000 meters per second and potentially up to 100,000 meters per second, depending on the design and the available power. So that represents an ISP of up to 10,000 seconds, or more than 20 times that of the best chemical engine. Wow! The thrust is produced by the reaction on the grids of the ions that are accelerated. The design is a bit more complex than the earlier Hall effect thruster, which you can kind of think of as being like a gridless ion drive. Although the achievable ISP values are much higher, the thrust that can easily be produced for a given size of the unit is lower, and the lifetime is limited by slow erosion of the grids from ions which didn't make it through. So we do really good GITs in the UK. Yeah, that's gridded ion thrusters. These took quite a few decades of research to get right at the Space Department of RAE Farnborough. The clip on the left is of a T5 thruster showing the grids, you can see them just there, the electromagnetic solenoids used to shape the electric field in the chamber, the neutralizer on the right-hand side, and the propellant inlet or anode at the rear, coming up now. Variants of this T5, which could produce as much as 70 millinewtons of thrust, but be throttled down to much less than 1 millinewton or almost nothing, have enabled some really exciting European Space Agency missions. So T5s and their neutralizers delivered the world's first fully electric orbit raising from LEO to GEO. They've flown the Gochi mission through the upper fringes of the atmosphere to map the Earth's gravity in extraordinary detail, and the bigger brother T6, able to produce well over 100 millinewtons of thrust, most recently headed in towards the innermost planet, Mercury. I spent a day in Farnborough with the T5's big brother, the T6, so the identical triplet to the one in the middle image enabled Bepi-Colombo European Space Agency mission to meet Mercury last year, which required more than doubling the already high delta V required just to go into Earth orbit. So a really demanding mission. And in the near future, similar designs, but made over in Germany, will be responsible for bringing the first samples from Mars, the red planet, back to Earth. How exciting is that? Here are some highlights. Some things I haven't talked about. FEEP, field emission electric propulsion, liquid metal droplets or sprays. Colloids, also known as electrospray, liquid droplets or sprays, just not metallic. Both well suited to the smallest spacecraft and starting to become a mainstream product. In contrast, the arc jet, older technology predating most HET systems. Arc jets offered a performance better than resistor jets, and many flew in orbit using propellant such as ammonia, but they needed more power than resistor jets, and the arc slowly erodes the thruster and limits their lifetime. I guess the three thruster types on the current Olympic podium are these. So Hall effect thrusters hatch can achieve very high thrusts. They get things places quickly, or at least as quick as you can get in the electric propulsion world. Colloids, small in every regard, inexpensive, but the high voltage engineering in compact spaces to make them work has been really challenging, so there's not much heritage yet. FEEP, after many initial challenges getting liquid metals to flow reliably in space, are making headway with European and US products flying, and they're reasonably compact, so good for higher performance small missions. Gridded ion thrusters still offer the best ISP performance, as I mentioned, but to really make them perform, you need a lot of power, not yet widely available in space, except for inner solar system missions like Bepi-Colombo, where the sunlight is stronger, and I guess when we finally get more widespread space nuclear power technology for outer planet missions. For the moment, gridded ion thrusters have only really been used for science missions. They've been beaten by Hall effect thrusters for commercial missions. Comparing the disadvantages then, so the higher performance of some of the more advanced forms of electric propulsion, in particular the gridded ion thruster, comes at the cost of complexity. Top left. For example, high voltage power supply units can be complex, difficult to engineer reliably, get them right for space, and they add significant inert mass, especially for small systems. You can see some of the voltages and currents that are needed in the image on the top left. The low thrust. Top right means there's an optimum exhaust velocity for a given maneuver time. Short duration missions or maneuvers, for example, to avoid space debris, pass through radiation belts quickly, or many defense applications will, with the possible exception of mag drives, tend to favor chemical propulsion. And of course, bottom right, the inefficiency in converting electric power to jet power or thrust means that larger missions needing fast maneuvers may need more power than is actually available from even the largest solar arrays. And there's a lot of heat management required when all that electrical energy is converted to thrust. All of this comes at the expense of system mass, bottom left. And of course, nuclear power in space to provide the energy for the higher performance, bigger EP systems, were it even available, raises other issues relating to mass, cost, and safety. So no discussion of propulsion would be complete without some consideration of cost. But you'd perhaps be surprised to learn how hard it is to get accurate costs for much of this tech. It does generally need to be tailored to the very specific needs of each space mission, which means unless you're actually an electric propulsion buyer for a credible space platform company, it can all be a bit of guesswork. Well, here are some real numbers provided by Thales Alenia Space, one of Europe's largest space companies. Up the vertical axis, cost in millions of euros. Horizontal axis, different approaches, starting from the old style chemical propulsion systems, CPS on the left, all the way to the most modern full electric systems with no chemical thrusters at all on the right. What does this tell us? Well, back in 2011, at least, more power was definitely needed to run high performance electric propulsion. Surprise, surprise. This power cost more, significantly more, almost as much as 5 times more from one extreme to the other, as did the propulsion itself. So if you're going to shift from chemical to all electric propulsion, and there are some hybrid solutions, you need to make sure the extra cost of the hardware are more than justified by the additional mission lifetime offered by the ISP. And that's just for starters. There's cost of time and cost of hardware need to be factored in as well. Interesting numbers though. So to finish off, electric propulsion, electric spacecraft propulsion separates energy source from propellant feed and potentially gives a lot more flexibility in selecting a propellant for its potential exhaust velocity. In reality, it's a lot more complicated than that. There are some good reasons to use electric propulsion. That's why the world's moving towards it, perhaps aided by a drive to having more electric power and better power processing technology as well. Some missions, such as launch from a planetary surface, rapid defensive maneuvers, and others, are probably never going to be able to use EP because the thrust will never reach what they need to be. That low thrust, not useful for getting into orbit, can be quite slow. Historically, a more expensive option and less suited to small missions, but that is changing. So, I'm Dr. Adam Baker, Rocket Engineering Limited and Cranfield University. Thank you for watching this video about electric spacecraft propulsion.